Okay, last video for chapter 4 and 28, we had left off talking about the electromagnetic spectrum, that electrons vibrate and create light. And depending upon the wavelength and the frequency, you have different forms of electromagnetic waves. So they give you a question like this on a test. Hey, here's the frequency of a light. What is its wavelength? What type of light is it? All right, so first of all, the unit, the hertz. Hertz means cycles per second. In other words, 1 over seconds. So in the case of electrons, it might be the number of electromagnetic waves per second. So if we have something that's 1.74 times 10 to the 17 hertz, that means that there's that many waves per second passing a given point. So we can use that information. Speed of light is equal to wavelength times frequency. We know the frequency. Let's solve for the wavelength. So we get speed of light divided by frequency. Now we can substitute in. Again, you don't have to memorize the constant for speed of light. I'll go 3 sig figs since the other thing is 3 sig figs. In fact, let's do this so it looks reasonable. Alright, frequency 1.74 times 10 to the 17th. And I'm going to do seconds to the negative 1 power. Alright, because that's what hertz is equal to. Now we can solve for frequency. So we get 3 exponential 8 divided by 1.74 exponential 17, and I get 1.72 times 10 to the minus 9 meters. And now we can go back to our electromagnetic spectrum chart, 1.72 times 10 to the minus 9. Or we could do 10 to the 17th for the power of the frequency. So we're somewhere in here. And let's go back and see exactly what we had. We had 1.72 times 10 to the minus 9. So I'm thinking 10 to the minus 9 is halfway in between, but 1.72 is greater than 1.79. So we're probably around here somewhere, but we're definitely in the X-ray area. So let's call it X-ray. And that'll complete our problem. So this is an X-ray. All right, Planck's hypothesis. And you got to understand, I've been mispronouncing it Planck for most of my life. And then I heard Morgan Freeman on Through the Wormhole call it Planck. Look, if Morgan Freeman calls it Planck, it's got to be Planck, right? It's Morgan Freeman. So anyway, light is given off in bundles of energy called quanta. In other words, light can act like a particle. Now, quanta is what we call an exchange particle. Forces all have exchange particles, one way of translating the force from one thing to another. Think of exchange particles like wealth. What would be the exchange particle for wealth? Well, it depends upon where you are, right? If we're talking about the United States, then we can exchange proprietary information, property, jewels, gold, but we do it in terms of what's called the dollar. Whereas in another country like Japan, you might do it in terms of the yen. So each atom has its own little exchange particle for light called a quanta. So we're going to shoot off bundles of quanta, which means that there's a certain fixed number of energy per quanta, but it differs from atom to atom. An electron, we'll just say atom to atom. So Planck was the guy who helped Einstein get his Nobel Prize in the photoelectric effect. Planck helped him out with the mathematics. Now, that doesn't mean that Einstein wasn't great in mathematics. He was. But Planck was one of the best in the world. And Planck had a little bit of hero worship for Einstein. And so he was more than willing to help him out. So Einstein winds up winning a Nobel Prize for what's called the photoelectric effect. Light can act like a particle. And Planck wins his Nobel Prize for this whole Planck hypothesis thing, the idea of light being given off in bundles of energy called quanta. So here's the formula: E equals h mu, which means the Planck the Planck constant times wave frequency. So you're not going to be required to memorize the Planck constant. We would give that to you on a test. But here's the type of problems you get. We find a quanta of light is found to have a certain amount of joules of energy. What is the frequency of this light? Well, first of all, let's go back to the Planck equation here. Is this a inverse or direct relationship? Well, it's direct. If we look at frequency, because this is a constant, we look at frequency. As frequency increases, energy increases. That's the whole thing with the Planck hypothesis. And let's go to this problem, copy and paste. There we go. Okay. So, photon of light, energy, there's only one energy equation we have in this chapter, and that's E equals the Planck constant times frequency. They give us the energy, but they don't give us the frequency, so they want us to solve this for frequency. So it's going to be energy divided by the Planck constant. And now we can substitute in 3.63 times 10 to the minus 22 joules. And that's going to be divided by 6.626 times 10 to the minus 34 joules per hertz. So in other words, joule seconds. Okay, so this is going to give us 3.63 exponential negative 22 divided by 6.626 exponential negative 34, and I get a frequency of 5.48 times 10 to the 11th joules. And that value seems incorrect to me, so let me just check this really quick. Did we solve for frequency correctly? We did. Let me see if I put it into my calculator correctly, because that seems like a large number. 3.63 exponential negative 22 divided by 6.626 exponential negative 34. And now I get the same answer, 5.48 times 10 to the 11th. Okay, the unit's not joules. It's seconds to the negative 1, which is hertz. Alright, so let's go to our electromagnetic spectrum chart, just for practice, to see what type of wave this is. 5.48 times 10 to the 11th on the frequency. And so let's zoom in here. 5.5 times 10 to the 11th, so we're somewhere in here. Halfway, but we're a little bit past that. So that's close. We're on the border between infrared and microwave. But if I had to guess, I would say infrared. We try not to do that to you on tests. We try to give you ones where you can clearly see what type of wave it is. But I think that this one is infrared. Alright, last type of calculation. Okay, suppose they give you this one. A photon of light. Now do understand, photon is the amount of a bundle of energy produced by one electron vibrating. It's only per one electron. And this particular electron vibrates and creates a wavelength of 500 nanometers. What is the energy of a photon of this light wave? Well, we've only had two equations. We've had energy equals Planck's constant times frequency, and we've had speed of light is equal to wavelength times frequency. Now they're giving me the wavelength, and then I need the frequency to go into the energy equation. So you can do this one of two ways. You can either deal with this equation first and then solve it for frequency, and then second, use the energy equals Planck's constant times frequency once you know the frequency to get the energy of that photon. Or you can do a little parametric equation. We can substitute one into the other. So in this first equation, and you can do this either way, I really don't mind. We're going to solve this for frequency, since we don't have frequency. That's speed of light over wavelength. So now we can substitute that in for frequency in the first equation. So energy is equal to Planck's constant, I'm just going to say Planck, times speed of light over the wavelength. Now the problem is the speed of light is in meters per second, and look what they're giving you here. They're giving you nanometers, so we're going to have to convert that. So let's do that first. So 5.00 times 10 to the second nanometers, and we know that there are 1 times 10 to the 9th nanometers per meter. So this is going to come out to be 5.0 times 10 to the minus 7 meters. So now I can substitute that in. All right, got my constant. And I got the speed of light. And then I'm going to divide that by my wavelength. Okay, so all my units cancel except for joules, which is good. Kind of shows that I'm doing it right. 6.626 exponential negative 34 times 3.00 exponential 8 divided by 5.00 exponential negative 7. And I get 3.98 times 10 to the minus 19 joules. And there you go. That's all there is for these wave calculations in Chapter 4. So, again, don't make it harder than it has to be. And I think I'm going to try to get some of these Chapter 5